Great. So good morning, everyone. I'm Carol Desnos, and today I'm going to present you the work on Gegelati. And the title of the paper is Lightweight Artificial Intelligence through Generic and Evolvable Program Graph. And this work was realized in collaboration between INSA and the IETR lab and the Silicon company in Rennes in France. So what are the three objectives of the paper? The first one is to introduce a new multipurpose reinforcement learning library, and I will explain that in detail. One of the key characteristics of this library that I want to present is also that it is an embeddable and deterministic parallelism parallel library. And finally, the third objective of the paper is to introduce the customizable aspect of this library. Unfortunately, due to time restrictions, I won't have enough time to present this customizability of the library, but I invite you to read the paper if you are interested in this third contribution of the paper. So, first of all, what is reinforcement library? In reinforcement library, you have an artificial intelligence called a learning agent that is interacting with a learning environment. And so by observing the state of the environment, the learning agent is able to react and to perform some actions on the environment, which will change the state of the environment. The state of the environment may also change because of time, because of randomness, or because of physical aspects. Then the state of the environment evolves, the learning agent has the ability to react again, and so on. For the learning agent to learn if it's doing something useful or not, we need to set up a third exchange of information between the learning environment and the learning agent, which is a reward. By giving a positive or a negative reward to the learning agent, the learning environment can help the learning agent learn something useful and to perform some useful action in the environment. So what are the technologies available for implementing such a learning agent? Nowadays, many people are using deep learning techniques or Q-learning technique to implement the reinforcement learning agents. What we are interested about in this paper is another technique for machine learning, which is Tangled Program Graph. A Tangled Program Graph, or TPG for short, is a reinforcement learning technique that was introduced in 2017 by Stephen Kelly and Malcolm Haywood from the University of Dalhousie in Canada. A TPG, so a Tangled Program Graph, is the model that is used to power the reinforcement learning artificial intelligence. This graph is composed of teams, which are the vertices of the graph, actions, which are the leaves of the graphs, and programs, which are the edges of the graph. In order to understand how a TPG works, we must first present how the programs inside the TPGs work. So let's have a look at the program. If we consider the program as a black box, each program will receive a copy of the state of the environment, it will process it, and it will produce a number as a result. And you should not try to give any meaning to this number, it is just a number written by the program. What's inside the programs? Well, the programs can be understood as an assembly program, which is a set of instructions. The instructions will work directly on variables from the environment. So here, for example, you can use the value of some pixels of the environment as the operands of the instructions, but they can also work on the results of previous instructions. The result produced by the last instruction of the program will be considered as the result of the program. So these are the programs inside the TPG. So how does the TPG work? To understand that, let's focus on an example of an artificial intelligence that is learning how to play a video game. And so the actions of the graph, which are the leaves of the graph, if you don't remember, each of these actions is associated to a set of buttons of the controllers or of the video game, for example. So how does this work? First, we receive a new state of the environment, which is a set of pixels of the screen. Then we start from the root team, so the vertex of the graph with no incoming edge. We start from this root team and we execute all the programs on the outgoing edges of this root team. Each one of the program will return a value, and then we simply select the highest value, which is called a bid, and we go along this path. we go to a new team, and once again, we execute all the programs of the outgoing vertices of the outgoing edges of this team. We select the highest value, and eventually we reach an action. We perform this action on the environment. The state of the environment will change, and then we restart the process again from the root team of the Tangled Program Graph. And this is how you execute a Tangled Program Graph. So we have seen how to execute a TPG, but how do we train them? We train them using a genetic learning algorithm. In a genetic learning algorithm, you start from a population of learning agents which have poor capabilities. And if you take back the video game example, they will have a very low score. And then through a genetic evolution process, and by selecting the most fitted element of your population at each generation, eventually you want to reach a population, a final population, where the score of the populations are very high by natural selection process, Darwinism at its best. So how does this apply to the TPG? Well, when you are training a TPG, instead of a single root team, you have several root teams. And if you execute the TPG from each one of these root teams, you will have a different behavior. And so you will have a different score. So what you do is you evaluate the score that you get from each one of these root teams. You get a score for each root team. And these are the scores that you get for generation N. When you want to prepare the next generation of the genetic evolution process, you just discard the worst performing team and you just kill them. You just remove them from your TPG. Then, to repopulate your graph, you will randomly select some remaining vertices of the graph and copy them. In order not to have the same behavior as the one you just copied, you will then alter this new root team by performing some mutations on some of their programs. And so you change the target of their programs, or you change the set of instructions of the programs themselves. And by doing that, you create new root team for your graph. And by evaluating them again, you go to the next generation of the genetic evolution process. So TPGs are great, of course, otherwise I would not be presenting them. TPGs have proven to be very efficient learners. They have an adaptive complexity, which means that the topology of the graph adapts itself to the problem in which they are trained, contrary to deep Q-learning techniques, which have a fixed complexity set by the designer of the deep Q-learning algorithm. They are very fast. For the video game example, for Atari video games, they were able to perform 2 to 3 orders of magnitude faster than deep Q-learning framework with the same performance. And finally, they are very lightweight. The storage capacity needed to store a TPG is around 100 kilobytes, while for similar performance, you need more than 50 megabytes for a deep Q-learning network. So let's come back to our implementation problem, because our purpose is to provide a library that implements TPG in a lightweight way. And one of our key objectives was for this library to be deterministic and parallel. Why determinist? Because determinism is a very good property when you have an embedded reinforcement learning library. It enables you to port an algorithm to train an algorithm on your computer and then deploy it on an embedded target. It facilitates the reproducibility of the results that you get. If you get good results on the computer, you will get them everywhere else. And it's also a great feature for debuggability. Then parallelism. Why do we need parallelism? Well, for 3 reasons: performance, performance, and performance. Performance of training, performance of inference, and performance of both combined. Unfortunately, parallelism and determinism do not go well together. When you try to design the parallel software, it will very often not be fully deterministic, and deterministic comes usually with sequentialism. So how will we achieve this purpose? To do that, first, let's see how we can get some sequential determinism. First of all, we need a pseudo-random number generator. A pseudo-random generator is a process to which you give a seed, a number, and from this seed, it will generate a sequence of apparently random number, but in reality, completely deterministic ones. So we use this pseudo-number number generator in the genetic evolution process. And so the genetic evolution process, which is responsible for mutating the programs of the TPG, will ask pseudo-random number to the PRNG. And again, we use the pseudo-random number generator for the evaluation process when randomness is needed in the evolution of the state of the environment. So this is how we do things sequentially. And then we can repeat the genetic evolution process, then the evaluation process several times to train our TPG. Unfortunately, what we want is parallelism. So let's see how we can achieve parallelism in a completely non-deterministic way. And this is the most naive way to get some parallelism. We just duplicate the genetic evolution process. And we give one instance of this process to each core of our target architecture. Because each one of the genetic evolution process will work on a different program in parallel in a non-deterministic order, they will keep asking pseudo-random numbers to the pseudo-random number generator in a non-deterministic way. And so you have non-deterministic mutations that are applied to the program. And the same is true for the evaluation process of the roots. You cannot have a deterministic process. So how do we get determinism? Well, the trick that we used to get determinism is to associate a pseudo-random number generator to each instance of the genetic evolution process. Using the main sequential PRNG, we give a seed to each one of these parallel pseudo-random number generation, and we actually give one seed for each program. And by doing that, we can make sure that the mutations that are applied to each one of the programs during the training process are completely deterministic, because the seed that is used to initialize the pseudo-random number generator of the parallel processes is itself determinist. And the same is true for the evaluation process. We just generate one seed for each root of the graph that is evaluated. So all of this has an overhead on performance, but as we can see on this first result, which is the speed up that we get. So on the abscissa, you have the number of cores that are used for the training process of a TPG. And on the ordinates, you have the speed up that we get when we go multi-core. And as we can see, the process, the parallel training process scales very well. And we get performance that are 20 times better on 24 cores than we got on one core, on an Intel core, on an Intel CPU with 24 cores. So this scales almost perfectly. What about an embedded target? Let's have a look at the Odroid XU3, which embeds an ARM big little architecture with 4 A15 cores. So on the A15 cores, we have a speed up of 2.3 on 4 cores, sorry, which in reality is limited by the bandwidth of the memory. We had a look at the result, and it seems like the memory is the limiting factor here. If we activate the A7 cores, then we can first see that on one A7 core, the performance is roughly half of one A15 cores. But the performance on the 4 A7 cores scales very well, and we get a speed up of 4 compared to one A7 cores when we activate the 4 A7 cores. Then we can activate any combinations of the A15 or the A7 cores. And the best speed up that we can get compared to a single A15 core is a speed up of 4.1, which once again on this chip is limited by the bandwidth of the memory. So to summarize, Gegelati, which is the library, the name of the TPG library that we have implemented, is a TPG framework for training, executing, and customizing learning artificial intelligence based on the TPG model. Gegelati is developed as a C++ library, which is both portable and deterministic. It works on Windows, Linux, and Mac OS. It is fully open source. The code is fully documented, and we have a very important continuous integration process, which ensures that we have 100% of the code that is covered by the unitary tests. We have some good features. We have some multi-core support, some custom instructions that are detailed in the paper, and many more to come, hopefully. We have several applications that you can already play with online. So we have the Atari video games. We have a physical inverted pendulum that you can play with, the MNIST classification problem, the tic-tac-toe two-player game. And we also have a robotic controller for a robotic arm with 6 servo motors. So, almost on time. Thank you all for your attention. If you are curious about Gegelati, you can check out the GitHub pages of the project. And otherwise, if you do not have questions right now, which I would be very happy to have, you can always contact me later to my email. So thank you for your attention.
Thank you, Carol, for the very interesting talk. Maybe if I can start, because I have one question. Where is the drawback here in this whole story? Because as you talked about this, it's a new thing for me. It's like everything is better than the deep approach. So is there any drawback here, or?
Yes and no. Okay. One drawback that I can mention is that, okay, we have very good results on the Atari video games. On the robotic arm and the inverted pendulum, we have very good results also. On the MNIST classification problem, so far, the results are not so good. We are not able to compete with the deep learning framework. So it seems like the TPGs so far are very good for the reinforcement learning problems. For other kinds of problem, we have ideas of why they are not working very well, but we still have to improve them. For the other one, okay, compared to deep Q-learning on these, let's say, quite simple problems, you're right, they have only advantages. They have no drawbacks. They perform very well as the deep Q-learning framework. And they are more lightweight. It's faster to train them. So no, it's true that they are better in in all aspects. If we really want to find some drawbacks, yes, for example, on the Atari video games, since the publication of the early results that showed that TPG were competing in performance with the deep Q-learning framework, Agent 57 has been published, which is a deep Q-learning approach that is better than any previous attempt to these video games, and it beats also the TPG's attempt. But this comes at the cost of a huge complexity in the training process and in the inference process. So once again, the trade-off offered by TPG between complexity and efficiency is great.
Okay, thank you. We have also one question from Eduardo de la Torre, or actually 2 questions. I will read maybe. First, nice work, Carol, and the questions. How well or bad does this scale up with increased complexity? It's the first question. And the second, have you tried crossover apart of mutation?
Okay, so for the scaling process, it scales pretty well. When you train a graph, you can see that the training process slows down when the graph becomes complex. But actually, this slowdown is not that huge. And the time, for example, on the Atari video games, the time it takes to train the TPG is still largely dominated by the emulation process for the video games. So the TPGs itself, the structure of the TPG is very simple. And even when the complexity of the TPG increases, which means graph with, let's say, at most hundreds of teams and hundreds of programs, it's still very, very fast to execute the TPGs. So the complexity is not a very big issue on the TPG side, even on complex problems. And about the crossover, no, not yet. At the moment, the only mutations that we tried were random mutations of the programs. So we swap instructions, we change instructions, we replace an addition by multiplications. But so far we did not try the crossover operation. We want to have a look into it, but we have this MNIST problem that is very interesting for us, and that we really are focusing on this right now.
Okay, thank you very much. I think we can have an interesting discussion on this issue also later. I'm personally also interested in this approach. Or maybe not I personally, but one of my PhD students should be. So thank you once more, and now